In this lesson, we're going to talk about oscillations and time and how different variables change over time. So let's consider a mass at the end of a spring during one complete oscillation. So we have a spring and it's hanging and it's at its most compressed point. We'll say its amplitude is at A at that point, and this is our time of 0. We're going to go to one full period over here where the spring has gone back to its original position, and our time is going to be capital T, that's our period. So what happens in between? The amplitude is going to change with time, and if you could graph it, the position versus the time, it's going to be a sinusoidal motion or cosine, depending on how you start the spring. But it's going to be a curved graph. So if we started it at the largest amplitude, here it is at its largest amplitude, the spring is going to move to its equilibrium position, and at equilibrium it's about a quarter of the way through its oscillation. So here it is at its equilibrium position is 0. Then it's going to stretch out to its maximum amplitude in the negative direction, and that will be at this point here. Then it's going to return to the equilibrium position here, which is right here, and at the very end it reaches its maximum amplitude again. The velocity will also change with time, and if you look at this graph, you can interpret what's going to happen, or you can look at the spring. So we know when it's at its most compressed point, it actually comes to a rest. So its velocity at that point is 0. Then it goes to its equilibrium position and it reaches its maximum velocity. But in this picture, its maximum, the magnitude is maximum, but the direction is negative. Its velocity is downward. So it has a maximum velocity at equilibrium. Then it's going to reach its largest displacement again. Now its velocity is 0. Then it's going to go back to equilibrium, and at equilibrium it's moving its fastest again, and then it's most compressed where its velocity goes back to 0. So when the amplitude is maximum, its velocity is 0. When it's at this point or this point or this point, it's not moving. When the velocity is maximum, the amplitude is 0. So it moves the greatest at this point or at this point, and those are where its position is at equilibrium. We can also look at the acceleration over time. The acceleration changes with time, also in a sinusoidal motion, but it's a little bit different. Remember, we said acceleration is not constant. Acceleration is going to be the greatest when it has the greatest displacement. So when it's most compressed or most stretched out, its acceleration is its greatest. So at its maximum equilibrium, we have the largest acceleration, but it's a downward acceleration, so it's a negative. When it reaches equilibrium, it no longer has a force acting on it, so it has 0 acceleration at equilibrium. When it is stretched out again, it has maximum acceleration, this time in the upward direction. So this will be maximum acceleration. Gets back to equilibrium position, has no more acceleration, so it's back to 0. And then it goes back to its maximum position where it has its greatest negative acceleration, which is right here. When the amplitude is maximum, the acceleration is maximum, but it's going to be in the opposite direction. If we pull the spring, it's going to be pulling the spring back to the center. So you can notice that the amplitude graph looks exactly like the acceleration graph. They're just flipped. They're mirror images of each other. When the amplitude is 0, the acceleration is 0. When it's at equilibrium, it has no acceleration. So if we could put this into a equation, this is what it's going to look like. This is going to tell us the position of our spring at any time using the variables that we know for oscillatory motion or for simple harmonic motion. So the position of our spring is going to be equal to the amplitude, that's the maximum it goes to, times cosine. So now we're going to use cosine to show where it would be on a graph. And the cosine is going to be of the angle, which is 2 times pi times the frequency of the spring times the time, and this is the time we're trying to find the position at that time. Now, The 2 pi should be your hint that your calculator for these problems needs to be in radians. Anytime we have 2 pi as our angle instead of 180 degrees or something in degrees, the pi is your hint that oscillatory motion uses radians. So you would take the frequency of the spring times the time you're trying to find times 2 pi, put your calculator in radians, find the cosine of that, multiply it by the amplitude. That'll give you the position at any time of your graph. So let's look at an example. Let's say we have a mass on a spring, and this is how its position is over time. So we have a few questions to think about. First, what's the period of this oscillation? Now remember, a period is the time it takes to do one complete cycle. So for this problem, we could look at the crest, which is the top of the graph. We're going to look at where it hits the maximum and where it hits the maximum. And this time in between is going to be the period. So we will say this is from about 14 seconds to about 38 seconds. So we say 38 seconds minus 14 seconds. That's going to give us our period, which is 24 seconds. Question B, what is the amplitude of this oscillation? So amplitude is its greatest displacement from zero. So our amplitude will be the height of this graph, which is about 4.5 centimeters. Part C, what is the position of this mass at 30 seconds? So we go to time 30 seconds, and the position is down about negative 2.5 centimeters. Part D, when is the first time the velocity of the mass is zero? Now be careful. Don't look for when it crosses the zero line. This is showing our position, not our velocity. So what do we know about the relationship between position and velocity? If the velocity is zero, that will be at its most stretched point when it's at its maximum amplitude, when it's at A or at negative A. So we're going to look for the first time when the graph reaches its maximum displacement. When it's at its maximum displacement, it has a velocity of zero. So that will be right here. It'll be about 2.5 seconds. And part E, at which of these times does the kinetic energy have its maximum value? So when is the velocity at its greatest? Because that'll give us the greatest kinetic energy. It's going to be traveling the fastest when it's at the equilibrium position. So we're looking for when the position is at zero. And this will be the first time it has the greatest velocity. It would be at 8 seconds. Now it's also at its fastest value at 20 seconds, at about 32 seconds, at about 44 seconds. This is just the first example, but it's also going to have maximum kinetic energy anytime the position is at zero. So far we've looked at simple harmonic motion, where energy is conserved and we have a simple cosine or sine graph. I just wanted to show you a picture of what's called damped oscillations. So in reality, if you did this in a lab, you wouldn't get a perfect sine graph. What you would see would be something more like this. It looks like a sine or cosine, but over time it gets smaller and smaller. It doesn't go as far because energy is lost to heat in the spring, to air resistance, to sound even. So when energy is lost, it's called a damped oscillation. Damped means energy goes, and so you'll notice that over time it'll get smaller and smaller. Eventually it will come to rest. In reality, energy is lost to heat and friction. A graph of these oscillations over time looks like this. Damped oscillations are when energy is lost.